So now we're actually going to run through some examples where we're going to find the area contained inside of polar curves. So first one we have is a dimpled cardioid known as r equals 2 plus the cosine of theta. What we're going to find is the area that is indicated here within the second quadrant. Now, as we're setting up our definite integral, one of the important things to point out is going to be what the bounds are on theta. You'll notice that we're restricted to the second quadrant on here. So labeling the angles appropriately that we know from back in trigonometry, we could express this region here as going from theta equals pi over 2 all the way up through theta equals pi. As such, we're going to set up our definite integral going from pi over 2 up to pi. Now, the area formula that we derived in the last video is 1/2 the definite integral of r squared d theta going from angle to angle. The 1/2 can either be inside or outside of the integral, it doesn't really matter. So for this area, we'll set this up as 1/2 definite integral. Limits will be from pi over 2 to pi. And the thing that we are squaring is going to be our r, which is 2 plus the cosine of theta, d theta. Now with that in mind, this would be the setup of the integral. To actually evaluate the integral, we'll need to perform some algebra. First algebra that we're going to do is to expand our square. That'll be 4 plus 4 times the cosine of theta plus the cosine squared of theta d theta. Now 4 has a relatively straightforward integral. 4 cosine of theta has a relatively straightforward integral. Cosine squared of theta can be integrated by using a power-reducing identity. Power-reducing identity for the cosine squared will be the following. Going from pi over 2 to pi, that part stays the same. This will be 4 plus 4 times the cosine of theta plus power-reducing identity for the cosine squared is 1/2 times 1 plus the cosine of 2 theta. We'll still have a d theta left over. Now at this point, we're going to distribute the 1/2 through the parentheses, and then we can take the 4 plus 1/2 that results and combine those as like terms. Pi over 2 to pi. And we will get 4 plus 1/2 is 4.5, or 9/2 once you get a common denominator, plus 4 times the cosine of theta, and then we'll get a plus 1/2 times the cosine of 2 theta. All of this with a d theta at the end. In this form, everything is ready to be integrated, so let's do so. We'll still have a 1/2 out front. Integral of 9/2 with respect to theta will be 9/2 theta. Integral of 4 times the cosine of theta will be 4 times the sine of theta. And 1/2 times the cosine of 2 theta. The integral of cosine of 2 theta is sine of 2 theta over 2, but with the extra 1/2 out front, that'll actually be sine of 2 theta over 4. Once again, going from pi over 2 all the way up to pi. Let's plug in these limits and see what we get. So 9/2 times pi, 9/2 pi, plus 4 times the sine of pi, plus the sine of 2 pi over 4. That's what we get from plugging in pi. Then we'll subtract what we get by plugging in pi over 2. 9/2 of pi over 2 is going to be 9/4 pi, plus 4 times the sine of pi over 2, plus the sine of, if we plug in pi over 2 to the sine of 2 theta, that'll be the sine of pi over 4. Now, several of these quantities are going to go to 0, which is really convenient for us. Sine of pi is 0, sine of pi is 0, and the sine of 2 pi is 0 as well. So we are left with 1/2 of, if I take my 9/2 pi and my 9/4 pi and get a common denominator for them and subtract, that'll be 9/4 pi. And we also have a minus 4 times 1. Distributing the 1/2 through, this will be 9/8 pi minus 2. Final answer for our area there. I did want to make sure we get plenty of practice with this, so I've set up another problem for us. Next problem is going to be, find the area contained in the inner loop of r equals 1 plus 2 times the sine of theta. Now, r equals 1 plus 2 times the sine of theta did show up in another video. This is known as a limaçon, and it looked approximately like this. So the reason that I know that the extreme point is in the upward direction is because we're dealing with a positive sign. So the area in question that we're looking for is right here. Now, we're not told what the bounds are, but thankfully in that other video we talked about how to get these bounds. These bounds are going to be created from where this thing crosses the pole, and then we'll be able to sweep out that area. So, crossing the pole is going to take place at r equals 0. We'll set r equal to 0 to get our two bounds. Setting r equal to 0, we'll have 0 is equal to 1 plus 2 times the sine of theta. If we solve this for the sine of theta, we get that by subtracting 1 and dividing both sides by 2. There are two places where it will occur that we wind up with sine of theta being equal to negative 1/2. That takes place at 7 pi over 6, and again at 11 pi over 6. So, with those things in mind, the limits of integration for this are going to go from 7 pi over 6 to 11 pi over 6. Same formula as what we just used on the previous problem. So 1/2 times r squared, this will be 1 plus 2 times the sine of theta, quantity squared d theta. Alright, we will need to expand this. Limits of integration will stay the same. That'll be 7 pi over 6 to 11 pi over 6, and expanding, we'll get 1 plus 4 times the sine of theta plus 4 times the sine squared of theta, d theta. Similar result to what we saw on the previous problem. After foiling this, 1 has a very straightforward integral, 4 sine theta has a very straightforward integral, the sine squared of theta will need to use the power reducing identity for that. That'll be 1 plus 4 times the sine of theta plus 4 times, and your power reducing identity for the sine squared would be 1 minus the cosine of 2 theta all over 2. Thankfully, the 4 and the 2 can be combined together. 1/2 definite integral from 7 pi over 6 to 11 pi over 6 of. If we take the 4 and the 2, that'll reduce to 2, and distributing the 2 through, we'll get 2 minus 2 times the cosine of 2 theta. We can take this 2 and this 1 and combine them together. So when all is said and done here, we will arrive at the following statement. This will be the definite integral from 7 pi over 6 to 11 pi over 6 of 3 plus 4 sine theta minus 2 cosine 2 theta. At this point, we are ready to integrate, so let's do so. 3 will become 3 theta. 4 times the sine of theta will become minus 4 times the cosine of theta. And the integral of the cosine of 2 theta will be the sine of 2 theta divided by 2. With the extra coefficient of 2 in front, that'll simply be the sine of 2 theta. Then we'll have bounds of 7 pi over 6 and 11 pi over 6. We're going to have considerably fewer things zero out on this one. We'll leave that 1/2 out front. We'll take 3 times 11 pi over 6. That'll be 11 pi over 2. Actually, you know what? Let's go ahead and keep that as 33 pi over 6. I predict we're going to have a common denominator in our future. Nope, you know what? It is going to work out nicely. 3 over 6 will reduce down to 1 over 2. So we'll call that 11 pi over 2 minus 4 times the cosine of 11 pi over 6 minus the sine of, this will wind up being 11 pi over 3. So that's from our first bound. Our second bound is going to give us 3 times 7 pi over 6. That'll wind up being 7 pi over 2. minus 4 times the cosine of 7 pi over 6. Then we'll see, oh boy, minus the sine of, if we double that angle, that'll be 7 pi over 3. Oh boy. All right, and running low on room there. Oh boy. Let's keep that 1/2 out front and continue to simplify these things. So this will be 11 pi over 2. The cosine of 11 pi over 6, this will be equal to root 3 over 2. Multiply it by -4, we'll have minus 2 square roots of 3. The sine of 11 pi over 3, if we were to get a coterminal angle, that would be 5 pi over 3. The sine of that would be root 3 over 2. So it'll be minus an additional root 3 over 2. Then we'll distribute the minus sign, and this will be minus 7 pi over 2. And that'll wind up being plus 4 times the cosine of 7 pi over 6. 7 pi over 6 is a quadrant 3 angle. That'll be negative root 3 over 2. Minus a minus, this will be plus the sine of 7 pi over 3. Coterminal to 7 pi over 3 would be pi over 3. Sine of pi over 3 is root 3 over 2. Not a whole lot of good stuff happening here other than minus root 3 over 2 and plus root 3 over 2 will cancel each other out, leaving us with half of, subtracting these, 11 pi over 2 minus 7 pi over 2 will be 4 pi over 2. That'll be 2 pi. Minus 2 root 3 and then a minus 2 root 3 will be minus 4 root 3. And then as we take half of both of those things, we will have pi minus 2 square roots of 3. Holy crap, that is good stuff. So, with those things in mind, let's try out one more example. Last example for us to try is going to be the following. I would like to find the area that is contained inside r equals 4 times the cosine of theta, but outside r equals 2. Now with that in mind, r equals 4 times the cosine of theta is a circle, and its extreme point will be in the horizontal positive direction. It will extend out 4 units. R equals 2 is simply a circle of radius 2, centered at the origin. So we have 2 circles of radius 2, just sort of staggered in the following fashion. We want what is inside r equals 4 times the cosine of theta, but outside of r equals 2. Now, based on the beautiful symmetry that I see associated with this problem, I think what I'd like to do is split this thing right down the middle and say I'm just going to calculate the area that's on the top side, and then I'm going to double it to account for the area that's on the bottom side. Now, with that in mind, we're still going to need to figure out the limits of integration. Now, normally we would do these 2 angles right here, where we see points of intersection between the 2 curves. But since we're going to cut this off right in the middle, one of our limits of integration will be at theta equals 0. Now, to get the points of intersection, anytime you have 2 curves and you're looking for a point of intersection, that'll take place when the 2 are set equal to each other. So that would be 4 times the cosine of theta is equal to 2. Solving for theta, we get cosine of theta is equal to 1/2, which occurs at 2 different angles. Those angles would be the quadrant 1 angle of pi over 3 and the quadrant 4 angle of 5 pi over 3. Now, a word of caution, you cannot set this up as the definite integral from pi over 3 to 5 pi over 3. That would imply that we're starting at this angle, going around this side to this angle. We do not want that. We actually would want to start at this angle and go up to this angle for all of this delightful area that's in here. So don't think of that angle as 5 pi over 3. Think of that angle as being negative pi over 3. That is, starting at theta equals 0, we simply go in the clockwise direction to get down to this angle. However, that's going to be a moot point anyway because we are going to go from simply 0 to pi over 3 and things should work out just fine. So this was pi over 3 right here. So our area is going to be equal to half of double what we get going from 0 to pi over 3. The half and the 2 will cancel each other out nicely. Now here we have the area that is contained between two curves. We have an outer curve, which is our r equals 4 times the cosine of theta, and our inner curve, which is r equals 2. The formula that we came up with was square the outer curve and subtract what we get when we square the inner curve. That'll give us the area between these two curves. The 1/2 and the 2 will cancel each other out. We'll be going from 0 to pi over 3. And this will be 16 times the cosine squared of theta minus 4. 4 is relatively straightforward to integrate, but 16 times the cosine squared will require the power reducing identity. Power reducing identity says that the cosine squared will be equal to 1 plus the cosine of 2 theta all over 2. And we'll hold on to that minus 4. The 16 and the 2 can reduce down to an 8. And distributing the 8 through, we will have 8 plus 8 times the cosine of 2 theta minus 4. Combining our like terms, we can take the 8 minus 4 and refer to this as 4 plus 8 times the cosine of 2 theta. Integrating this from 0 to pi over 3 will give us the area that's contained between these two curves. Integrating 4 with respect to theta will give us 4 theta. Integrating 8 times the cosine of 2 theta will give us plus 4 times the sine of 2 theta. This is going from 0 to pi over 3. Plugging in our upper bound, we are going to get 4 times pi over 3 plus 4 times the sine of 2 times pi over 3. So 2 pi over 3. Plugging in our lower bound, we'll get 4 times 0 plus 4 times the sine of 2 times 0. Good news is, all of this is a lot of 0. So we simply need to evaluate what we have over here. This would be 4 pi over 3 plus 4 times sine of 2 pi over 3 is root 3 over 2. So final answer for this one is going to be 4 pi over 3 plus 2 square roots of 3. That will be our final answer for this area.